Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Good. At the end of today, you should be well equipped to do assignment 2, and then we will actually be doing a bit of recapping as well as a bit of polishing over the last 3 weeks. But there's even better news. In 2 weeks' time, we've got a new room. A room that's big enough for all of us. It's a flat room, and it's set up with lots of tables so teams can sit together and actually do some work in a workshop setting, which is what we wanted at the beginning but didn't get. So, double reason for celebration. Hurrah! So this is what we're going to do today. We'll have a little bit of a recap on where we're up to. And then we should have a look at the last 2 topics in information systems about how to drag this whole thing together. Let's begin. I thought at first that my little Mac was doing something strange. But this string of text is actually Latin, and it's the ANU motto. It's the motto for the university, which is nice. And it comes from this book by Lucretius, who is an ancient chap. And this is what it means. It means, first, study to learn the nature of things. Study to learn the nature of things. Before you do things, actually find out something about it, is what this is all about. And the reason I put this up is that that's what we do when we are modelling systems. When we are modelling a domain, finding out who's in it, what's in it, how everything works, unpacking it, finding out what the concepts are. This is exactly what we're doing. We're studying to learn the nature of the thing. So this is just spot on for ANU's motto, and a very nice little ancient book it is. Now I thought I'd just put up one slide because a number of students have asked me about how do I find out material for doing my assignment 1. You know, where do I start? So we talked about concept mapping, and the next set of questions was, well, where do I get my concepts from? Well, the answer is you get them from the literature. So searching the literature, there's a good place to start. The library is good at this, and they've got a help desk. You just wander up and they give you all the help in the world. You say, look, I'm doing an assignment on blockchain, don't know what it's all about, and the librarian will give you a hand. I don't know if it'll be any good because librarians don't know anything about blockchain, but they know a little bit about searching, so they may be able to assist you. Here are your main sources though, of course. Google. Google gives you lots of interesting grey information, very useful. Wikipedia, wonderful place to start to get a feel for the overview. Google Scholar, which is where you can locate academic papers on these topics that you're searching for. The ANU library, access to e-books and journals, so you simply go to the library search site and type in whatever you want, and up pops all sorts of things, many of which are accessible online. So things that are in library databases tend to be a whole lot more reliable and of greater quality than what's in the web and what's in Google Scholar, because the university has explicitly selected this material as being good quality stuff. I use the Oxford English Dictionary quite a lot as a good place to start when I'm thinking about a term. And it's a good source of terms, as is WordNet. So when you're using search terms, use quote marks. So I gave an example in one of the discussion forums. Who here is read a discussion forum. I mean, I had a look at the discussion forums, and they're really not read by very many people. There's a whole rich set of stuff in that discussion forum about your assignments. Read it. Anyway, there's a whole bunch of stuff there about giving examples of the use of quotes in searching and the different sorts of things that you find. Astonishingly useful. Synonyms, use a thesaurus to find out words which mean something similar, and then balance stuff, searches that are too broad. Search that produces 400 million hits, isn't that useful? A search that produces one hit, isn't that useful? You need somewhere in between. And I'd recommend you set yourself up a little research workbench. This is just part of my browser. I've just got a drop-down box that's got Library Scholar, the OED, WordNet, the UC Library, I work up there as well, the ADFA Library, the National Library of Australia, Microsoft Academic Semantic Scholar. So these are just some of the sites I regularly use when I'm looking for things. They're all just set up there as links, so I just have to click and go. You're going to be doing this a lot over the next couple of years. So why not tool up for it? Instead of addressing a blank screen and saying, what am I going to do? Just go down to your Dropbox and start. So set yourself up a little research workbench. Neat. So that's all I was going to say about how you might address the literature. Now, where have we been? Oh no, yes. Where are we going? Yes. So you know this little diagram so well. We've done some architecture, we've done some conceptual modelling. Now we're going to do a bit of systems. And that should set you up pretty well. That's where we're up to. And this is a little grid that we were using at the end of the last lecture. Down the bottom we had the world, all the physical stuff in the world, which we started with our little man looking at the universe. Then we looked at the input process output model as a way of thinking about technical IT architecture. That every bit of IT fits into this neat little model of IPO. You can interpret any bit of IT you like using that model. That's all the physical stuff. That's world one, of course. Then we started to look at the rich picture to give us an idea of what an overall system might be like. So the rich picture. And this is world three. It's thinking about the concepts, the stakeholders, their interests, the big ideas in the domain you're going to be working on. And then we had a look at metadata, that is data models, SG relationship diagrams, different words for the same thing. We looked at data models and we looked at actual data. You might remember your student data that you derive from your student cards. That's the actual data, as different from the data model, which identifies the objects and the attributes of interest. So here it is. Here is our grid. Here is the overall picture of what we've been doing for the last 2 weeks. Let me just fill in a few pictures just to cement this in your mind. So here's our IPO model. Here is the physical world being sensed. That's a little picture of a motion sensor. This is a little picture of a servo. That's the kind of thing that affects the world. And we send a message to a servo, and our little robot does something different. Inputs and outputs. Here's a little laptop, inputs and outputs. And up here I put a little picture of a router, which is just a way of inputting and outputting to a network. Same deal, inputs and outputs. Processing units. Well, here's a little picture of a CPU, central processing unit, sitting on a part of a printed circuit board. Pretty ancient, but still. That's the physical processing unit. So we're talking here about physical componentry. And over here, our storage, IPO, the storage, the USB and hard drive. There is physical components of an IT technical architecture. Lovely. Here's our little robot. So if you put all of this stuff together into one nice little package, you might have a robot which has all of these devices in it. Then we turn to world three. We turn to the conceptual part of it. We said, right, systems can be captured by a rich picture. We can use a rich picture to start identifying a domain of interest. And for you, in assignment 2, it's the Kangaroo Island energy system. And then we said, right, well, let's do some data modelling, and this is a little picture of the data model we did for students and courses. And here's a little table of a database that we did with the student data in it. So here's our total picture of what the system is, instantiated with little examples of what we've done. See, we've done a lot in 2 weeks. We've galloped through this. We've tackled everything there is to know about IT architectures and the technology, and we've tackled all this conceptual modelling as well. Terrific. There's 2 full undergraduate years of work in that, so well done. And where to from here? Well, tonight we're just going to do the missing portion, which is how we do software and how we think about processes and activities within systems. And that will complete the whole picture of what an information system is. And once you've got a complete picture, you can apply this picture to assignment 2, and you can generate the advice that the council needs about all of these components that their system will actually have. It's beautiful, isn't it? Bravo. That is so good. Okay, that's where we're up to. So let's have a look at tasks and modelling. Here's our 3 worlds model. And I want to just talk about these 3 things very briefly. We've started to talk about data, information and knowledge. And I'll put a couple of papers into the readings on this. So world 3 is data and information and explicit knowledge. By explicit knowledge is meant anything that is written down. So I've got one of my mum's recipes for how to cook a beef Wellington. Nice little recipe. And it lays out all the steps, one by one, about how to prepare this dish. Good. That is a bit of explicit knowledge. It's know-how. But it's not in my mind, it's on a bit of paper. It's not until I read it and say, oh yeah, I get that, that it becomes tacit knowledge. So once it's read, it's there in world 2, inside somebody's mind. It's there, part of their brain, part of their mind, ready for action, ready for use. So here's the distinction between explicit and tacit knowledge. Data, we know all about data. Information is any kind of a statement which embraces data, and it embraces explicit knowledge, and explicit knowledge is know-how, codified know-how. Okay, there's a little model, a task. A human task is a little process or set of actions that you do in one sitting. Coming to this lecture is a task. It has a beginning point, you do it in a sitting, and it's over. Working with this semester is not a task because it goes for a long time, it has many different tasks that make it up. So a task is just an activity that a human does, or a machine, that starts and stops in one sitting. And just like the IPO model, which is another example of it, it's input, process and output. It's a model we can apply to this idea of a task. So that's the process layer. What are the inputs to a human task? Well, you get documents about something, you may get data relevant about something, you'll do something with that and you'll produce new documents and new data. So, you're doing assignment 1. No, assignment 1 isn't a task, it's a process, because you're going to do lots and lots of different tasks to make up to generate assignment 1. Let's say you say, well, I today am going to research blockchain history. I've given myself an hour. So what you've got coming in is a document that says I'm going to research about blockchain history and no data. That's your input, your task. You do your searching, you use your know-how to accomplish the task, And what you produce is a set of notes about the history of blockchain. That task is now done. You do this again with different kinds of aspects of blockchain, and then further down the track you'll have another task which says, put together the skeleton assignment. What you'll have here then is sets of documents about different aspects of blockchain, and your task will be to bring these together and create a brand new framework that brings it all together, and then you'll produce a new document which is our first draft of assignment 1 with some of these notes in it. Neat. So a task is just one of these things that you do, an activity you do in a sitting which takes some input, does some processing and produces some output. Lovely. To achieve this task, you need some of these things. You need know-how. Your experience and attitude has a lot to contribute to the way this task is done. If you're feeling cranky about it all, you will do a bad task if you finish it at all. Knowing how to, well, maybe you don't know too much about how to do this task, but you give it a go and you learn a lot in the job. And once you've completed a task, there will be feedback, because your experience will be being built simply by the act of doing the task. So that knowledge will be being built. But in addition to that, you've got all this World 3 type knowledge. You've got procedures, policies, ways of doing things, tools and techniques that you can deploy in order to do this task. You may have a procedure that is how to write assignment 1. You can imagine a procedure that's all nicely written out. Actually, I've got one, but I haven't shared it with you yet. Later on. You might have a procedure that's all nicely written out, and that might assist you in doing this task. You might have done this task before, and you can find precedents. But this is not just about you. This is about organisations and just about anything. So, in the case study, for example, there will be tasks to be done, and there will be a history, a record of what's been done in this task in the past. This task has been done in the past, and you can use that in order to improve the way the task is done this time. And lastly, there's a whole bunch of organisational context that fits in when you're doing an organised task within a business or the government or whatever. Doing an organised task, there's all this stuff that surrounds it. There's a little picture of a task. The important things are it uses the IPO model, it adds knowledge to this, because you need knowledge in order to do a task, and it adds a bit of context, organisational context to the task. So, a task. Are we good? Yeah. How do we specify how to do a task? So this recipe of my mum's says step 1, step 2, step 3, step 4, step 5. It's a simple recipe because it just goes straight through from the beginning to the end. This is a bit unusual. Here is an example of a flow chart. I imagine you've all seen flow charts. They're used a lot for all sorts of different purposes. A flow chart simply says you start and you end, so that sounds like a task. You do something, order a burger, you ask a question, do you want fries? Yes, order fries. Want a drink? Yes, order a drink, pay the cashier and end. So here is a simple task represented as a flow chart. Here is how to do that task. The boxes mean do something. The diamonds mean answer a question. The lines mean and then. So it's order a burger and then ask the question, do you want fries? If the answer is yes, then order fries, and so on. So the line means and then, or and then do, something of that kind. So what I've just done is to tell you what the syntax of this model is. The syntax is a description of each of the components of the model, the kinds of things that are in the model. And one of our big problems in modelling is that modelers often leave out what the syntax is. So particularly in business papers, academic papers in business that you see, you'll see some of these wonderful diagrams about how things operate. And they'll have different kinds of arrows, some big, some fat, some dotted, They'll have different kinds of boxes and circles and bubbles and all that sort of stuff, and they never tell you what these things mean. And that's because they don't know. They're just drawing up a picture. They're not trying to actually model this seriously at all, which is a tragedy. Why don't these guys just do a bit of concept mapping and sort themselves out? Why don't they get their ontology right so that they know what they're talking about? No, I think it's terrible. Seriously terrible. Anyway, nobody listens to me, so, except you have to. So here it is. Here is a very common way of specifying a process. This is a bit of know-how. You know how to order a burger. Here's another way. This is a decision tree. So when things get a bit complicated, you can say to yourself, oh, I don't know how to make this decision, so I'll build a little decision tree to tell me. So this decision tree says, I want to calculate how risky a particular loan might be to someone. So here's what I ask. What is the income? Is it one of these three different sorts? If the income is very low, then immediately this loan will be high risk. No further questions. If the income is very high, then let's have a look at their credit history. And if the credit history is good, then, okay, this is a low risk loan. It's moderate risk if their credit history is bad, because they've still got plenty of money even if they don't know much what to do with it. And if we don't know what their credit history is, we'll treat it as though it's okay, because presumably if they've done something wicked, it'll be there on the database saying this person's done things that are wicked. And the guys in the middle, okay, middle income people, let's check their credit history, and if it's bad, then they're high risk. If it's good, then it's moderate risk, and then so on. So what they're doing here with mapping a more complex decision is figuring out what the factors are that need to be taken into account, and then drawing up a decision tree to try and figure out how we're going to make our decision about the level of risk. And that's all it does. It could be done in a table. You could do it as a whole set of statements. If this and this and this and this and this, then that. But really that's really hard to read and hard to use. This is quite easy to read and easy to use. So each of the lines means branch out depending on the value of the variable. That's all these lines mean. And the last box is the answer, the result. Now, many years ago, I built a little system here in the ACT to look after driver's licences and vehicle registrations. So when people want to register their truck, they'd ring up the motor vehicle registry to ask how much it was going to be. And they said, the motor vehicle registry had difficulty answering these questions because determining the registration fee had about 7 different factors that went into determining the fee. Lots of different factors, and they were unusually arranged. So this question could not be answered on the phone. Oh, crikey, this is no good. This is not customer service. So what we did was we built a little tree just like this, 7 wide, and we printed it off on a huge piece of paper, visible from a distance, put it up on the wall behind where people answered the phone. So somebody rang up and said, I've got a truck, how much is it going to cost me to register? The telephone operator was able to say, how heavy is the truck? 2 tonnes. Is it for private use? Is it under hire purchase? And work their way down this, through the tree, until they got to the end, $487.60. Boom, boom, done. Excellent. Lovely little way of representing that reasonably complicated bit of knowledge. This is answering the question, how do we calculate risk? Or in the case of the traffic, how do we determine the fee? And here is the answer. So, another specification of knowledge. What we're doing here is we're specifying how to do something. When we were talking about data, we were talking about what exists. What is there? in this world that we're interested in. So that was what exists, and this is what can we do with it. Here's another example. This is an algorithm. Find the discount. If the order is from an individual, and if the order is blah, 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 then this, or else this, which is another way of representing that decision tree. So this is just written out step by step. And we write out these steps like the recipe in just a linear form, and that works really well for simple cases. It doesn't work too well once the things start to get complicated though. Once you've got loops in it, so oh hang on, go back to step 3 if you've got yourself a problem. That starts to get a bit awkward. Does anybody here play the piano? No? No, well, it's just that in the piano they've got some interesting notation for where you have to go once you've played some phrases, because often the piano piece is made up of many different, or many repeats of phrases. So rather than simply put them one after the other, it says, oh, we've only got this much for this bit of music, but you do that, and then you do this, and then you do that again, and then you do this, and then you do that again. So quite reasonably complicated. All of this is a struggle to find out how to represent it so it's useful. It's all how-to knowledge. Okay, now given that we can start to specify tasks in terms of how to do it, how do we tell a machine how to do something? Because what we're trying to do here is to specify tasks in such a way that if we know how to do it, we can tell the machine how to do it. So when we're talking IT, this is the go. All of those methods of specification work more or less well with human beings, but if you want to automate it, then you've got to have a way of communicating this to a machine. So we do this through computer code. And here are 3 different kinds, or 3 different sorts of programming which allow us to tell a machine what to do. The first is procedural programming. Are there any ex-programmers here or people from an information systems background who know about programming? Good. Well, this is a typical bit of programming code. This is written in a language called COBOL, and you can just read it. It says move T work to current work type, process each transaction until we get to the end, do something, search the table, move 0 to that, when that is equal to that, compute this, ... add this to that, input this, output that. So these are instructions that are codifying those ways of specifying a task, codifying it so a machine can actually do it, and the machine can just execute this code. So that's nice. This is procedural programming or algorithmic programming. This is an algorithm. An algorithm is just a specification of a way of doing something, and this is done in software, so the machine can do it. That's procedural programming. Now this is declarative programming. And what this says is, let us simply declare some facts, and these are some facts. John is the father of Jim, Jane is the mother of him, and here are a couple of rules. Person 1 is a person of parent 2 if person 1 is the father of person 2 or person 1 is the mother of person 2. So this is a definition of some relationship in the world, and these are facts about this little world. Now this is a language called Prolog. And what happens with this is that if you ask it a question, who's Jim's father, the reasoner in Prolog simply uses these patterns here, and tries to instantiate them with this data and come up with an answer. And it'll come up and tell you, well, these are the answers to your question. Because we know who is Jim's father, well, This says John is the father of Jim. So here's the relationship, father, John, Jim. Who is Jim's father? It simply looks through the database saying, where's the relationship father? Where's one that has Jim as the second term? The answer is John, and it comes back and tells us John is the father of Jim. So what this has is a bit of general purpose reasoning, that is something that knows nothing at all about the data or about the domain, but it does know that if there's a pattern that looks like this and data that looks like this, here's the answer. It'll allow you to reason over anything. Now this is precisely what I was talking about with conceptual graphs last week. You remember the case of the conference being held here in Canberra, and I was laying out what all of the concepts in this conference were, and there's Fred writing paper number 27 and all that. That conceptual graph, that way of thinking about the concepts in the conference, can be represented to a machine in this format as declarative programming, and it simply executes. The machine answers any question you like. This is very different to an algorithm that we were looking at before, very different to this procedural programming, which does only precisely what it was told to do, step by step by step, finish. This is a system which is just ongoing and just answers questions, and the more it knows, the more of these facts it knows, and the more it knows about the relationships, the better it is at it. This is the kind of programming that they use in games to play chess and to play Jeopardy and all that sort of stuff, and beat humans at it, because the reason is a whole lot faster and the database is of infinite length. So this sort of technology is better than humans. Cool. The third sort of way that computer programs actually do things is through artificial neural nets. Now, this is a picture of a neuron. This is a picture of the kind of thing that right throughout your body. Your body's got about 10 billion of these neurons in your central nervous system. These are the things that do all the work for you, and they're really simple. These dendrites are input sensors. This is a processor, and this is an output sensor. If you stimulate the inputs, the processor thinks about it and will produce an output or not, depending on what sort of inputs it's got. This is a natural cell which fits the IPO model. Takes its input through dendrites, processes it in the stoma, and produces a signal on the axon. If you put a few of these cells together, you get a picture something like this. And here we've got two of these neurons, one here, one here. This neuron is attached to sensors here, sense organs for sight, say, or touch. So that if this is touched, those sense organs fire. This is the input, hits the soma. Soma decides, hang on, this is interesting, sends a message down through its axon, which is input to the next neuron along the way, which is an effector neuron, which sends a signal to a muscle to do something. So this is a map of a reflex action. Remember the examples in assignment 1 of reflex action, where you're riding your push bike, your eye sees a fly coming towards it, and automatically you blink. Your eyelids close without any thought at all. This is how it happens. You've got a sensor, you've got a neuron which takes that sensor, thinks about it, and says, danger, danger, fires off a message to your eyelids, and they close. This is how it works. And this is modelled in our information technology systems. We have sensors to sense the outside physical world. We have these, they are processors, so these are processors, they take this input. The output of the first process is the input to the second process. The output of the second process is to do something in the world. So here's your body and information technology doing completely analogous tasks. So the third form of ways of getting a computer to do something is to mirror that neuronal activity. And here's how it's done. What we do is we build a whole bunch of hidden neurons. We build a bunch of sensor neurons and an active neuron. And you can have many layers of this thing in between. But we don't tell this what to do. We show it. So we just set this up. It knows absolutely nothing. And then we give it some data. We tell it what the value of these variables are. This is actually a diagnostic system, so it tells the system one case where the cancer cells had these attributes and the diagnosis was that it was a cancer cell of a particular kind. It tells it one case. And it sets up, the system sets up for itself the weights between these neurons, what's important and what's not. And then we give it another case, and the system modifies those weights, and another, and another, and another, and another, and thousands of cases, tens of thousands of cases. So we train this network to actually come up with the right answer. So we're training this thing, just like you would be trained if you did your violin practice. You're training your body to do something, which is just getting your neurons to work in a particular way. We train a neural net in precisely the same way. And that's the third means for going from a specification to a computer being able to actually act. Follow an algorithm, do some reasoning over its data and thinking type patterns, or do something that we can't account for, this neural network. Because with neural networks, they can't tell you why they've done it. With the other two methods, they can tell you why they have come up to the conclusion they have, because they're both symbolic. But the third one is not. It has no idea how it got to that answer. It just says, this is what I reckon. And isn't that actually just like humans? We do precisely the same thing. We come up with answers with absolutely no way of knowing how we did that. We rationalise it afterwards. You come up with an idea and say, oh yeah, I worked that out. You know, I used the logic. You didn't. Your brain did that for you. It presented you with the answer. And then you went back and tried to figure out, how can I talk about this? Or how can I think about this answer? You justified what your mind had done for you, subconsciously, using your conscious mind. Does that seem fair? Come on, give us a nod. All right. So, we're talking about doing processes, setting up a process for an information system. We've talked about tasks. Now we've talked about how a computer can do those tasks. A human can do the task by reading the explicit knowledge and following it, as well as having their own experience. A computer can do it by that explicit knowledge being coded up in a computer language and it executing that computer language. So a computer can do it. Now let's move up a nudge to processes. So a process is just an assembly of tasks. Here is an example, writing a paper, task 1, task 2, task 3, task 4, task 5. Go through this set of tasks. Now, unlike a recipe, this is how to do a dinner party. So this might be prepare the entree and put it in the fridge and prepare this and then prepare that and then lay something out and do this. So it's a set of tasks all put together in a sequence in order to produce an overall process. Cool. Individual tasks being structured. Here's an example of a library system. A bunch of tasks, one after the other, to actually buy books for the library. A bunch of tasks, one after the other, for people to borrow books from the library. There's a little database sitting in the middle of all of the library books. The library acquisitions puts data into the database. The circulation system drags data out from the database and puts more data back in. Here is our automation boundary. Inside the blue line is a computer, and outside the blue line is humans. So inside the blue line we have computer programs that do their part of the task, and we have our database to support what's going on. Outside of the blue line we have humans doing their side of the task. So this is an automation boundary, and the users are outside. Let's have a quick closer look at this boundary. So there's the information system on that side, the humans on that side, and here's a line that goes through between these different tasks. And at each of these intersections we have an interface. This is the interaction between you, the user, and the machine. So behind each interface is a task that the machine is doing, algorithms or whatever. Here is the interface, the things you see on the screen, the things you touch on your keyboard, and here's you doing some human part of this task. Booking an airline flight, for example. You come into this point, make me booking, and you know what you want to book. You've done your scans, that sort of stuff. You start talking with the booking system. You know various things, it knows various things. It's dragging on its database. You're looking at what you want to do. You work it out across the interface, pay your money, and that's the end of that task. Humans and computers working together through that interface. Computer programs on one side, human processes on the other, human thinking on the other side. And here's a way of representing the whole shebang. It has a bunch of tasks, a bunch of flows, external sources of syncs, and a systems boundary. So this is the automation boundary again, just another picture of what might be happening inside. A bunch of tasks and a database.
Sorry, Craig, the previous slide there's use cases there.
Oh yeah, use cases. A use case is a bit of a technical design jargon. A use case is a case of a particular use of a machine. So you can use a machine for all sorts of different purposes. If you specify one use case, it's how do I do this particular task using this program. That's a use case. Trying to think of an example here. But if you ever come across the term, why don't I actually Google it? Use case. See what it says. I'd be quite interested to know. Is that fair enough? That's all that means. A use of the machine. Now this is a way of specifying a process which is a bit more complicated than the others, but more useful. Across the top here we have who does it. In the body of the form, the body of the specification, is like a flowchart. Here are processes and decisions. Things that flow between these activities in an activity diagram are documents. So for each person, they know what they have to do when they receive a particular document. They're the tasks, these are the documents. This is a way of specifying different people doing an overall process, being part of an overall process, and here are the steps that each individual goes through. And to give an example of that, here is that little model again. And this is a product called Bizaji, which is just a piece of software. And you can give this model to a piece of software and it will run your business for you. This is called a workflow system because you've set up what the tasks are and who has to do it. You just have to tell this software, this is what I want, and it produces it for you. Bit of smart software. But you can implement this process model just as we implemented the task model. So we implemented task model as a set of how to do a particular task. This says you can also do it with a process. Here's how to do a particular process. That's enough from me, more than enough in fact. Would you like to do a little team exercise? This is our little process model. What would be nice is you're all doing assignment 1. No, let's make that assignment 2. You're all doing assignment 2. So in your teams, work together and produce a little map that looks like this for the process you are using in assignment 2. So the stakeholders will be each of you and me and Wattle. They're all stakeholders in this. So try and figure out what the tasks are, who does what, and what the relationships are, and what the flow is like. So, let's spend 10 minutes, a quarter of an hour, doing a little process model for assignment 2.
This is correct. I'm not sure. With the assignment, the educate stakeholders in a project with stakeholders, we discuss the strategy for the assignment and we choose a topic and then we choose our individual topics as well based on the assignment.
Good, so just put in the screw like this.
Teacher, professor. Correct. I have no idea how to apply this method to our assignments.
Oh, good. You won't be alone, so why don't I talk to everybody before we go through it?
You will
We'll
talk
just, yeah.
later.
No, right now.
Right now?
Well, ladies and gentlemen, let's just have a look at the top level, do a couple of bits of this, and then you can carry on. The reason we're doing this exercise is that you'll probably build something like this into assignment 2 to explain how the process of managing electricity is conducted, what the tasks are, how they're related. So you'll need to know how to specify a task or a process. So what I did here was just to set up my stakeholders, the actors. There's me, here's Waddle, here's students 1, 2 and 3. And I don't know who other actors there might be, but they're pretty obvious ones. So here's the first task, publish assignment 2. So I wrote assignment 2 and I gave it to Waddle. Waddle stored it away and presented it. Then, here's the team, grabbing assignment 2 and having a team meeting. And from the team meeting, they decided that various people would go away and do different things. Try and find out about electricity systems, try and find out about Kangaroo Island, try and find out about previous work that might have been done on electricity systems in Kangaroo Island. So they're all tasks. And then you just keep building on from there. How are you going to bring these together? What other tasks need to be done? And at the end, submitting your assignment. Well, it depends. This is a very interesting question. The question was, Wattle's not an actor. It's just a filing cabinet. Which is kind of right. Is it an actor or is it not? And these are decisions that you have to make when you're doing this sort of modelling. Are there actually tasks that are done by this or not? If I take Wattle out, how is it that a student meeting gets this document? There has to be a mechanism. So these are up to you as a designer to think about who the actors are and what they have to do in order to be successful. But certainly the last step of this will be me giving feedback. Here's me giving feedback to the team. The question is, what goes on in between? This is a boundary between a machine and a human.
But humans are humans, right?
The humans are all on this side of that line, and everything on that side of the line is computed.
Why does this arrow point of human and computer interface changes well?
It's pointing to the blue blocks. The arrow is pointing to the blue blocks.
Actually, not even humans are here as well.
Humans are on the left-hand side of the blue block. And
Because for making document, we also have to interact. So even if the flowchart flows like this, it doesn't mean that they've separated this part for computers and this part for humans, right? Like the boxes.
well, it does, because here we've separated out what one human is doing from what the machine is doing from what the other human is doing. So what we need here is what computer programs on that side, we've got humans on that side, and we've got this interface in between. So this thing here is the interface.
Every task has a border of humans.
Yeah. Oh no, it means that, oh yeah, you're right, I see. These are some sorts of humans and these are other sorts of humans. This is a swim lane, so that might be an agent or something like that. And this might be something that's making a book. That's a good question. It should have the heading on the top like that. Good point. I'll fix that. Well, shall we start again? Okay, good. So what we're trying to do here is just get a bit of a grip on the idea of doing a process, specifying the process. And in the Kangaroo Island case study, there will be processes that the system will have to do. And for you to specify those processes, you're going to need a tool, and this is a good tool for that, because it'll have various kinds of actors on it, and various kinds of activities that these actors have to do in order to complete a process. So now, that's that story. Let's just have a look at a few things that you might have come up with as far as assignment 2 goes. Can you identify some activity, some task that isn't on the diagram so far?
Give lectures.
Good. Thank you. Give lecture. What happens to the lecture? Ignored. No, don't worry about that. Move on to the next thing. It's got to go somewhere. So perhaps this student takes the lecture and does some work on the data. What data will our system require? What data? What other tasks did you come up with? Tasks that you are going to do in order to produce assignment 2. Oh, well, you're going to have some difficulties in doing assignment 2 if you don't know what you're going to do. It's going to be awkward. What's the last thing you might do? Exactly. You might submit it. Submit it to Wattle, and it comes to me for grading. I'll give some feedback, which will go back out to Wattle, to the team. before you can submit it, what do you have to do?
Choose a topic.
Well, you've got a topic. This is assignment 2, so you know what you're doing.
For a specific topic, like what we are presenting our case, do a research on it.
Yeah, well, okay, let me put that up. This person's going to do some research on what?
On the web and Google and all other.
Yeah, but to find what? Information about? Anything in particular? About Kangaroo Island, for example. Somebody's going to have to do some work on Kangaroo Island, aren't they? And somebody's going to have to do some work on information management systems that look after electricity. So, an electricity management system, somebody's going to have to do some research on that, aren't they? So read the posts in the discussion forum, which goes in some detail about the kinds of things that you're going to actually need to research and understand in order to produce your assignment. What comes just before submitting your assignment? Yeah, you've got to produce the thing. Right, excellent. Record video. There's the whole team doing this process of recording a video or making your PowerPoint with VoiceOver. What do you have to do before you can get to that point? What do you have to do before you can record your video?
You have to prepare slides and notes.
Yeah, exactly. Thank you. You've got to prepare slides and notes. Speakers' notes. And somebody's going to have to research how to do a video. How many of you have made a little video before in a formal life? Yeah, exactly. So for all of the rest of you who haven't done this before, you're going to allocate someone to find out how do we do a video. That's a task that somebody's going to have to do. Find out how to do the video. And then that will feed in to how you actually go about recording it. So what we're doing here is we're building the activities that you're going to have to do in order to submit this assignment. And it's not minor, is it? I mean, there's heaps of stuff that we haven't looked at between the start and the end of this activity diagram. So the second half of this unit is all about project management. And this is exactly what that is. This is building up what activities we have to do in order to complete this project. We're setting up the activities. And we're figuring out who's going to do them and in what order, how they're going to feed through. So this is just a process spec of how we're going to do this task, or this assignment. And there's a bunch of tasks to be done. So you can see that it isn't actually that simple. There's quite a lot in it. So the more you plan and do, each one of these tasks produces an output. So if you haven't got an output, you haven't done the task. Each one of these produces an output, and that output becomes part of your final submission. So you do all your research. You do some research on Kangaroo Island. You find out leads of information. That will feed through into your assignment. This will feed through to the assignment. That'll feed through to the assignment. So every little task you do is building your assignment. You don't wait till the end and try and produce something, because that is a path to failure. You're supposed to be doing it right now. Okay, are you convinced that this is actually a reasonable thing to do? Well, that would be good. I'm not sure that I believe you, but it would be good. Okay, now, the last thing we need to put in place before you can finish your Kangaroo Island assignment is something to do with systems and bringing the whole thing together. So let's just do that now, and then we'll go into a decent-sized team meeting in order to try and knock this assignment on the head. So here is our little model of what we're trying to achieve. Here's our physical world. Here is our IT world, part of the physical world. We've now got ourselves some process designs like that, how to do a process. And we know that we can build the tasks into software if we have to, if it's an automated system, or we do human activities if it's a human system. Cool. So, here I've colour-coded these. That's not very good, is it? I've colour-coded these categories of World 3 from the very beginning. I've said there are three. There's data, there's all this text, and then there's this structuring kind of stuff. And part of that is because we have different systems that address these different parts of World 3. We've got data management systems that address data. They're our databases. We've got information management systems that address our documents. And we've got knowledge management systems that address our knowledge. And over here on World 2, we've got our AI technologies which actually execute. So we'll now just take apart the different systems that you might find in a comprehensive organisation. These get integrated into the one big system, which is a part of an organisation. So here in Kangaroo Island, this is the Kangaroo Island Energy Management Information System, and this is the council and everybody else that's on Kangaroo Island. So this system becomes integrated into those organisational entities. Our purpose in information technology is to mobilise data and information and knowledge so that a user can do a decent job. That's our task. Our task is to get a user to do a great job by being well informed and knowledgeable. So that's what systems developers attempt to do. So here's our task. We'll just have a look at some data management, some information management and some knowledge management. And here they are. Firstly, pardon me. So a system is a structure of components which has some sort of emergent properties, and we'll talk about these sorts of systems: transaction processing, management, information systems and so on. That's what we're going to talk about briefly. Transaction processing. Well, this is the sort of system that you use very regularly throughout the day. Every time you buy something, you do a transaction. Every time you log on to the system, you're doing a transaction. A transaction is just something that records a particular small event that happens. Highly structured. If you buy something at a shop with your credit card, then that transaction has a specific structure and stored away on a database. And you get the statement at the end of the month. A routine day-to-day activity that generates vast quantities of small amounts of data. High volume. Increasingly we do transaction processing ourselves. We're the agent at our cards and things do it. In the old days, organisations used to do the transaction processing. So they used to go to a bank to do something. The bank would do the transaction for you and give you the money, but now you just do it all yourself. Transaction processing systems. Now, you can think of some transaction processing systems that will happen in the Kangaroo Island case. People will pay bills. Power will be generated. Power will be consumed. Power will go to a battery and come back out again. These are all transactions as these things actually happen. That data will be recorded. Management information systems look at the transaction processing data over a period and tell management if there's anything odd happening, finds exceptions, and it gives up reports. So guess what? Today we did more transactions than we've ever done before in our life. This is the product of a management information system. It just takes all that transaction data, it summarises it, or it finds exceptions in the data saying, hang on, look at this. Here's somebody that used their credit card for $1 million, when in fact, you know, those are the exceptions that management information systems find. So there's a cluster of functions or tasks that a machine does which does this sort of work, and that we call the management information system. It's the one that I can do searches on to find out who's in this class. So everybody that enrolls in the class or withdraws from the class, every time they take an act, they're there on the database, and I've got a management information system that lets me say who are the participants in this class, who's withdrawn, who's still active, ... And it gives me these summaries, or it gives me lists, and that's all done through the MIS. Executive information systems are like MIS systems, only they're for people further up the chain, and they are longer term, and they oversee what the whole organisation is doing, typically through a dashboard, something like this, which has a whole bunch of different metrics that are coming from different parts, different MIS systems within the organisation, and aggregating them and presenting them as a dashboard. So typically these things range over a number of years, and the executive information system does trend analysis and tells you what is happening, how things are going. Now this is the sort of thing that boards use, so one level up from management to the executive level and the board level. EIS. Business intelligence systems. These are getting more interesting. These business intelligence systems are the ones that try and find out interesting peripheral information, not from the transaction database, but from other sources. So, internally, there might be data mining that goes on, which is looking over your database, trying to find unusual trends. This is not MIS, because MIS is only concerned with things ticking over and being under control. This is trying to find out whether there's anything unusual going on. Data mining. Business intelligence systems also gather information from the outside world, outside of your systems. So they go to web servers to find out what the competition is doing, to compare prices, for example. Your business intelligence system does these searches for you. It comes up and says, guess what, your competitor just down the road has just dropped their prices, and you might want to respond to that. That's what your BI system will do for you. So it's got this internal look, and it's got this external look. And it also just scans the environment, looking for anything that's unusual that's happening. So it looks for new business organisations that are coming into your patch by looking for government data of things that have been approved, for example. So business intelligence. Lots of AI goes into business intelligence, lots of smart support, and lots of data analysts. So if you go to seek.com and have a look for the sorts of jobs that people in IT do, you'll find lots and lots of data analysts and data scientists, and this is what they do. They try and find out what AI systems need to actually do, what they need to find out. A decision support system is another type of information system. The decision support system has a model in it of how an organisation operates, or some part of an organisation operates, and it allows us to run that model thousands of times with different possible scenarios to tell us what might happen at some point in the future. And next week we'll have a look at how this is done, and we'll have a look at a restaurant model. This restaurant model shows how many staff are on, how many customers, how much car parking there is, when the menu was last changed, and other sorts of factors, and it builds a little model of what's related to what. Then, by playing with the variables, what if we get an extra 100 customers, what would happen? And the model will run, and it'll tell you what it thinks would happen. And this allows you then to change the model, or to find ways of getting more staff involved or doing something or other to try and solve this problem if it arises. So decision support is about making decisions on the basis of a model and lots of possible data. So you might use decision support systems that are not automated to make decisions about what you're going to do. Well, obviously you do. So just coming here, I imagine many of you would have had a spreadsheet with lots of dollars on it and lots of different possible universities and different factors, and given that some thought, and you might try varying a few of those and coming up with some results about where you might go. Or maybe not, but that's a DSS, a decision support system. An information management system, as different to a management information system, looks after information. It manages information, and this is about documents. It's involved with document description, indexing and retrieving, and processing using document management techniques like browsers and document management systems. There's a whole suite of different sorts of systems that manage documents. These are separate from systems that manage data, database systems. These systems manage documents. And lastly, knowledge management systems. And these are about trying to find out what we know and how we might codify what we know so that we can mobilise it and people who do tasks can do them better, or a machine can do them. And lastly, we've got physical control systems. And this is the kind of system, all of these systems are active in Kangaroo Island. And this is the kind of system that actually does the hard work of interfacing the information system with the actual electricity that's flowing around the system, a physical control system. And here is an example. This is a waste management system. What we've got here is rubbish bins, garbage trucks, an incinerator, some landfill, and a whole bunch of other things. These are all physical parts of a waste management system. We generate waste, we put them in rubbish bins, they get collected by a truck, they get sorted, they go to various ways of trying to get rid of it. A physical system. But wait. Now, if we want to manage this system using information and information technology, there it is. We put our little system there and shrunk it. Guess what? Here we go. Lots of people. These are the users, the managers. They say, we want to manage this system. What comes between us and the actual physical reality of rubbish and garbage bins and things like that? What can we do? What can we do? And here's the answer. Here are all the sensors. Lots of sensors on garbage trucks. What's being picked up? How heavy is it? Sensors on garbage bins to say this garbage bin needs to be picked up, or this garbage bin is too heavy, or what. Sensors throughout this physical system to detect attributes of what's going on there. These sensors feed through an internet. Down here are our whole set of different kinds of information system working from this database and those sensors. And here are lots of different users using those systems in different ways. So here are our different systems. Here's how we get data in and out, the physical type data, and there's lots of in and out type data from our users as well. And this is the total systems architecture. And I can well imagine your assignment having some ideas about the physical electrical system on Kangaroo Island. It'll have some ideas about technology that will measure what's going on physically. It will have some systems in order to process, think about that data, run simulations on it, more about that next week, do other kinds of activities to support the various users and their desires. These guys will have featured in your rich picture. What they're doing probably features in your rich picture, you know. We want to make sure that we don't have a power outage, blah, blah, blah. Rich picture stuff. Here's the data that you'll be thinking about. what data we're going to have to store, transaction processing systems to get that data in, which includes the sensors and that sort of stuff, management information systems, what's actually happening, executive information systems, here's all the trends. They'll have lots and lots of paperwork flowing around the organisation. That's all got to be managed with your information management system. This is it. This is kind of a sample answer for assignment 2, because it has a very physical system with sensors, all sorts of different systems, all sorts of different users. It's wonderful, isn't it? It just brings together everything we've done in the last 3 weeks, weeks 1, 2 and 3, all built into this little model. Yeah.
Here is one quick question. Like, would all the systems come under the second one, right? So all the systems are going to come under the 1, 2, and...
Well, just a word on models. When you have theories and models, they are never compatible. They are always views onto something. So each model that you ever use, and I don't mean here, I mean any theory that you come across in any subject, will be a view onto some complex situation. Different models take different views, perhaps of the same situation, because they'll emphasise different kinds of variables and just see things in a different way. So don't expect these models, these theories, to be compatible. They're just different ways of looking at things. So this is a way of looking at this system which is a specifically information system oriented view. Because this is a total system and it's got subsystems and it's got IPO and it's got physical stuff, it's got data stuff, it's got process stuff, it's got users, and all of this stuff is linked together to produce something bigger than any of the other components, The system brings together lots of things, structures them, so that something can be done which can't be done with any of those components individually. A system, that's what a system is. Something with emergent properties, an organisation of a whole lot of components which operate together in order to produce some emergent property, something different from all of those components. That's a system. Right, well, what I was going to suggest was think about your progress with your technical IT architecture, your rich picture and data model, that's those weeks, and then start thinking about this. That's this week. Those are our topics that we've gone through in the last 3 weeks, and they all add up to that. Oh. And you will need that. Well, that's it from me. We now have an hour to have a team meeting and start pushing ahead with your assignment, and I'm here to wander around. I am losing my voice, however. Just have to take a seat. Yeah.
For the assignment, you mentioned a lot about this kangaroo identities. We thought we were using our own topic and we went to learn
Assignment 1. That's assignment 1 where you choose your own topic.
assignment. We were fixing it for kangaroo identity. We started with the 2%
in some respects, yes. What did that mean with these slides? Like some of that, it's got to be your own role. Yeah, that's fine. But I'll just look at this slide and then I'll go over the previous slides. Yes, you build your own conceptual framework. Absolutely. Well, you'll build yours, but you'll be using other people's ideas. Or you might even find one that you really like, that you think is really useful, and you say, okay, well, the conceptual framework is really useful. So I'll do this and this and this, and I'll actually have to change it a little bit. Fancy stuff that it doesn't account for the law of vocabulary. Good. That sounds good. Yes. And we'll just do a bit more on it, as much as you can. I think you need a reference for them. I reckon if you've got more than 10 or 12 references, you're probably going too far. If you've only got 6, you're probably too few. Somewhere, yeah, somewhere that's a good sum of numbers. Have a look at the movie by Robot. There's a movie called Robot. Just have a look, jump onto Netflix or something and have a look at that movie. It shouldn't cost you anything. It'll change your mind. And this one. Yeah. So that's what we've learned in the last 3 weeks.
And so this is the whole system architecture is about we are going to. So this overall system architecture. And this is
That is the last point.
the last point. And so what about what we learned last week about the data?
Yeah, what's this bit? So that little disc there, that's there.
Yes. Here, the data is sorted by the information system that we learned with this week.
Yep.
And
And in order to know what that is, you've got to do your data modelling.
data
So that's where
modeling,
your data modelling comes from.
or the data modeling is for the shortage part.
Yeah. You model the data you need, and that gets stored in the database. Here's the data.
And this is last week part.
Yep.
And the whole architecture is IPO input or process.
Inputs coming from there and from here.
And
Processing here.
Processing here.
Outputs coming from there and there. The system might say to a truck, go over there and pick up this load of rubbish. The sensor has come up and said, there's rubbish to be picked up here. So the system sends the truck.
Both these two ways are input.
Both of them are input and output.
And output. And the process of shortage is data.
Yep.
I get it. And another question is about the assignment one. And so it's about concept analysis. So, and I'm not quite sure about what I'm going to find out. Is it what the concept really is and the characters?
Yep. Characteristics of it. Yep. The effects of it. There's a little list of subtopics that you might think about.
And
In the assignment, I've written out a list of things. These characteristics of the topic.
so are we going to talk about the concepts all around this? For example, I talk with cybersecurity and I'm going to talk about the concepts around it, like cyber threats and defense.
Yeah, it's right, yeah.
And
There's all sorts of things you could talk about. So you just got to do your searches to figure out what it is that you want to talk about.
and so the conclusion and all the outcomes, the characters of this concept.
So that somebody who doesn't know anything about your topic, like cyber security, will read your paper and then they will know all about it.
So this is my paper is a map for the wide interested in cybersecurity at all.
Who don't know anything about it. Yeah.
I'm going to show them the directions and what it is.
Yeah.
Well, and the last question is about the draft that we are going to submit this week. So is it's a draft of the whole paper or is it just a conceptual map?
You can submit wherever you're up to, but the more the better. Because if you've done a heap of work, you'll find the next few weeks to bring it, to make it into a nice assignment, will not be onerous. But if you've hardly done anything, then the next weeks are going to be hard, increasingly difficult.
And so this is my
Nice.
map.
Very nice.
So it's about cybersecurity and this is connected by the parts and objectives to software. And so there's something like history. I don't know what the connection is between my copy. It's got something there.
Well, keep thinking about it. If you can't find anything useful, say, people do talk about history, but I'm not going to. So you address that in your assignment.
That's all if I miss some part.
It's best to recognise that the literature talks about it, but it's not pertinent to what you want to say about cyber security. Every cyber security assignment I get will be different. Students will select different aspects to be interested in, and they'll drill down a totally different path of a very big topic.
So the topic is that just choose the part that we are interested in and because something to say.
Yeah,
Don't need to complete all the things.
you can't. It's too big.
Oh, that is thank you, Professor. Good luck.
Keep talking.
Like basically
The next one. Yeah.
so we
I know you have to do your own work, but this is an example.
I mean like all the
You don't have to follow an example. I mean, the example is, here is an idea or a set of ideas, and here is an example of it. Now you're over here, you've got a different pace to work with. So some parts of the example will be similar, and some parts will be really totally different.
Yeah, I know. I just do something similar like
I know what you mean. So the answer is yes, but not too similar.
yeah, absolutely. And I also want to know for the data model, do you want to like we give a lot of examples what kind of data we need for this,
Yes.
and then put it into a form?
You don't have to worry about that. It's enough to say there is storage,
Yep.
and your metadata defines what that storage will
So
look
can we
like.
like do a little bit extension over here and to put our data model over there?
Yeah. Or you can have it separate. You can treat this as your physical, as your final system, and then this top part is the specification of this system.
Okay, I got it. So for the rich picture, is the rich picture similar to this?
Well, this is a particular kind of diagram. It's an information systems diagram. And a rich picture has things like all the stakeholders in it, which are not on here, all of the stakeholder ideas, or the big ideas of the system, like in Kangaroo Island's case, it's energy sustainability. You won't find any of those kinds of ideas in this. This is about implementation, it's about how, and that is about what.
Oh, okay, I got it. So the rich picture is basically like the overall idea.
So have you Googled rich picture?
Yeah.
Okay, so you know that it's about the overall ideas. It's not about how. This is about how. They're useful ways of thinking, but this is what we will certainly need.
So this slider must be used.
Yeah.
Another question I want to know how to use reach feature by slider.
Well, have you written up, have you done some research on this picture? Found out what they're used for or what they look like? Have you done some research? But you need to do some research. Research this picture. Find out what they're used for and what they're like. And then you'll see that the system you are thinking about Kangaroo Island has to actually match in some ways that this picture. That system tells you how the sustainability is going to be met, how stakeholders are going to be satisfied, all about how and what they all produce electricity. Your system is the one that manages the electricity. You don't have to worry about too much about solar, for instance, and the energy production and all of that. But you do have to know how much electricity they're producing. Oh, yes. big ideas are what everybody's interested in. Why are they going to do this? That's what those are doing. Make it yourself. So you've got the tool, you know what, that's just how easy you're trying to all that stuff. And you go figure out how to present it nicely to the person. Where does that come from? Depending on what you want to use it for. What do you want to include? Here's the one what do you... Well, we do things to show. So what does this show? Does it show the face of our at the moment? Are there things here that will drop out and come out? Yeah, but the question is, why was the reader interested in that? Why would the reader be interested in that? Yeah, why are you interested in that? Because that is what we're about. So I'm interested in the history of AI, and here it is. What is interesting about this? Why are you telling somebody else that this is interesting? And it's interesting to you. Why should I be interested in this? What's important about this? Yeah, oh yes. So one of the conclusions is how AI might be used in kangaroo wildlife. That's probably the best part of your assignment. So, understanding of this topic, AI, and then why this is relevant to kangaroo wildlife. So if you think about this history, are there things in that that is relevant to understanding AI? If you can find out why you think that, you'll be a step ahead. Why would the history is interesting? That's a good excellent. There's one idea. Here's the history, and then we can see that as technology has changed, so AI has changed. And AI has caused new technologies to be created. So, what's going to happen in the future? Exactly, so this timeline is in the past, up to the present, you now push it forward. But what technology change might happen? What might happen with AI? That's you using the history. Yeah, from your perspective. That's you using the information you've got to do something interesting with it. Very well. No. What you do on the assignment one is you interview individually, and at the end of assignment one you'll say, guess what, this might have an effect on kangaroo wildlife like this. And then assignment two, you'll only have some kind of evidence, only that's the assignment two. So it's technical
For the characteristic of my application, yeah, can just we use language application. Yes, we share. But in the end, and just use
Yeah, you've got to talk about it. You can't just put stuff in there and expect somebody to try and understand it.
to show the way process, the recognition, possibly some about it.
Yeah, so you introduce it.
And just regarding as the final
Well, your final conclusion can be about how data science might affect kangaroo island. That's really you start writing your final.
and just handle it like this.
I don't know, I'll have to see it. You can't do it in words. Once I see the draft, I'll be able to tell you something about it, depending on what you think.
We'll have some suggestions for it.
That's the plan. You submit your assignment, your draft on Friday. We have a look at it and give you some feedback. Yeah, to get it back early in the following week. Early in week 4, so we still got plenty of time to think about it before the end of week 6. Yeah, there are only examples, but don't go into lots and lots of details about that. Because the topic is AI. So stick with AI. Here's an example, here's an example. Another form of AI has a different sort of example. People are on the own game. AI. Data science. So I'd like to hear it. So I'd like to hear what you how you decide to do.
Do I get marks if I include everything?
It depends how you use it. If you can actually introduce it, if you can look at the context about the type of security, like this, so that but I'm going to concentrate on this one. So you've recognised a big field and you concentrate on just a part of that field.
Oh, so I can do it like that. Suppose I have cybersecurity as my topic, so I could talk about cybersecurity, but just for the instinct, I do need to mention that there is cyber law as well in that.
Yeah.
There's a part of it.
Yeah, so you start off with a broad brush, explaining what cybersecurity actually is, and explaining the topic. And then you take the bit that you specifically want to do, and all those in detail.
And I have one more question regarding the cybersecurity in Gado Island. Do we have to go to the background check of the Gado Island as in, like, to know the loopholes and everything happening in the Gado Island? Because there's so many things which are happening right now, I just saw it. So there's,
Absolutely.
yeah.
Yeah, looking at similar systems is exactly the right thing to do.
Because there is actually a boat thing going on which is needs to be constructed in Gado Island, even the cable ties and everything. So do I need to include everything? Or
Yeah, you don't have time to include everything. But you don't have space or time to do anything. But you may well find some similar system which is just like the one the kangaroo island needs. And your problem's going to be solved. Yeah. You may find such a thing.
I tried finding it, but I couldn't get it.
Oh, that's a shame. Oh, I'm sorry to hear that. So you've got to get stuck with doing all the work.
Yeah, so
Oh,
the thing is
that's
that I can do it. I researched about it, so there is not a perfect system for that thing. But I guess we have to look for the loopholes and everything, drawbacks, and then find a system for all this, like according to the intelligence. Is that the thing we have to do?
Yeah, well, you'll have to bring up risks and problems, I would have thought. How are we going to cope if position breaks down?
Okay. Thank you, sir.
And then you might think about what the problems are with it and what people are saying about it and what the use of art and once you start searching for that, the military is very big in drones. They have a lot of interest in drones, so you might have to talk a bit about that. Not just about delivering coffee or anything like that. And then you've got to say how drones might be used in general environment for the electricity system. So you're trying to see your, the electricity system and describing the electricity demand system. And drones may well have a part to play in that. So what part to describe how it might work in the same material.
First assignment is supposed to do basically I thought I should talk about what IoT is first in the beginning.
One of your problems is that you haven't got anywhere near enough text.
Yeah, I mean, this is the cloud
other words, you're missing out on a lot. You've got no references from but you've read things.
Yeah.
And you haven't used them. You've wasted your time.
So, I mean, I don't have my entire example such as now.
Every time you go looking for something about
IoT.
I'm not doing hours work on IoT. The stuff in the when you find something useful, you start writing it. And you put down the reference. And you do that every time, and you will have you won't be just playing around with is this all right or am I on the right track? Forget all about that. You've got to be on the track before you can be on the right track. Here's your hand. Thank you. Over here, the data science looks quite different in this circumstance. So that's the way you do it, rather than saying here's data science, here's example 1, 2, 3, 4, 5. Here's one aspect of data science, here's a good example of that. Here's another aspect, here's a good example of that. You've got to find the aspect of data science that you're interested in, and then how close to the assessment. No, it doesn't come close. No, nothing to do with assessment too. No, just get on with data science. So what is data science?
Data science.
Well, yeah, you've got to answer the question. You've got to answer it. And there are lots of different ideas about what data science actually is. I'll show you one. Yeah, look at this. Right. That's interesting. What is that? Data complex science. That's very interesting. That's from a university in Europe. Well, I mean, if you want to know what data science is, here is one of many places to look. Data science is somewhere in there.
Is it a rich picture?
Yeah, well, sort of. A rich picture shows stakeholders and big ideas. This is more of a concept map. These are concepts, and here's
Venn diagram?
Venn diagram. Yeah, exactly. Yeah, that bit of it is. And these bits are just add-ons. So what I did, I just did a search. I added this term ECF because it's the European competency framework. So I'm doing some work on this at the moment, and it's about jobs in computing. So this has lots of jobs for data scientists. Have a look at seek.com. Yeah, here's another one. Look. Data scientist.
This job posting website.
These are all jobs, yeah. Here's a job for a data scientist.
I don't know the requirement for the data science people.
Yeah, well, it'll tell you something about data science. If all these people are being recruited. It'll tell you a bit about what they do. So that's what you need to do. Browse around, discover.
I'm faculty.
Well, it may or may not be appropriate. It may or may not be actually useful. So this reading trade, where does that come from?
It's from the
Oh, the Satori, right. Okay. Yeah, Ogden and Nash is coming from. But look, you should be going well outside the readings. Yeah, you should be using Google and Google Scholar. You've got to, which topic are you doing?
cybersecurity.
Cybersecurity. You've got cybersecurity. Don't stick with what we've done in class. A technique for doing concept analysis. Yeah? We talked about doing concept analysis. Last week we talked about doing concept maps. Take cybersecurity. Go out in the world.
A social process and read some I think it's deep in the master.
Yes. There are all sorts of things. The world is a very rich place. You've got to choose the bits that are going to work for you.
And I see the discussion on the food.
Good.
And I see this is really, we talk about this paper which that said, show what actually the answer it is. I mean, the paper is just explaining
Just explain all the concepts in cybersecurity.
just
And then say how it can be used.
so I just simply explain this by words. So I
The
don't
diagrams are always used.
I don't think concept maps. So I don't need actually need a title like this.
There's nothing specifically you can do. You've got a bunch of models that you might find useful. So cybersecurity, you might find that you have a physical network that you want to say, oh, cybersecurity means looking after this particular in this physical network. So let's just have a quick look at that. So given if you've got a model like that, you might say cybersecurity has to look after this node here because that's a place where it can be hacked. Cybersecurity has to look after this line because that's a way that people can tap in and trap that data that's coming, or else put false data in. And you've got to look after this, you've got to look after that, you've got to make sure cybersecurity that people don't hack these little laptops. So you can use a diagram to point out where in a system cybersecurity is really important. And you can do that with one diagram and one paragraph of text. It's powerful. It says, guess what, cybersecurity, the physical aspect of cybersecurity is like this. You just explain it. Right, good.
And parts except the physics, other parts just explain like that.
Absolutely.
Perhaps I can.
You can.
few slides I'm not quite clear about the method, and the information is slide is 3. I think when you start from here, I also asked my classmates, most of us are not quite clear about these 3, these 2, and start from this slide, what you want to explain for us, what kind of information you want to give to us.
Right. Well, this is about a process, how you might specify a process.
Yeah. Actually, you just mentioned for the some side is for our task, and for this side is for the information system. So when we combine, you want to mean is like a process or something. What do you want to teach us from this slide?
These slides tell you how to represent your understanding of a process.
Okay.
So
That is the process when we touch from the. Okay, I think for here is like the humans, and for here is like the storage, the data, and for this part is for the data, and for this part is for humans. When humans touch with the data, is like this the process for human in charge of the data, and for this side, we don't quite understand what these 2 slides mean. I think it's so far.
So 2 shouldn't be. Right.
Yeah, start from here.
So
No, this one I got it already.
So
It
we know about how to do a task.
I understand, and I understand.
Now,
Yeah.
we want to put the tasks together to do an entire process,
Okay.
like this. A whole bunch of tasks,
Yeah.
and that becomes the process. How do we specify is the question. And you could, if you wanted to, just jump straight through to that. Here's a way of specifying a process.
Yes.
However, you may see diagrams like this, which also show a process. And they show different aspects of a process. They show users, the computer, processes, tasks that are done, and data that's stored. These models don't show data that's being stored. So this can be useful if you want to demonstrate that there is data being stored within the system.
Okay. So for this one is another explain for the how we can for the process, and for this one is like just you mean it's like a task or like a storage?
These are tasks.
Yeah,
this is
task.
storage.
This storage.
Yep.
And this means how we can process to the task.
Yep.
I see. I got it.
And it's the same with this.
This one is also means.
This is person A and person B. This is a travel agent, and this is you doing your bookings. This is a booking information system.
This is book
And
information.
this is people doing their part of the work.
Okay.
There's an interface, a screen, and keyboard, and behind is the little computer algorithm that's doing its work.
Oh, I see. I got it. So this is present for the process. Yeah.
Yep.
The blue.
So this is a process, and it's half done by machine and half done by people.
Oh, I see. I got it. Okay. Thanks. Thank you.
As much or as little as you like.
As little?
As much.
As much as.
Or as little as you like. No rules.
No limitation or no standard.
No. Now, ladies and gentlemen, we have a class in here at 4. So what I'd like to do is to take further questions outside. Is that all right? And I'll just clean up the boards and things like that. So I'll talk to you outside. Things that the lecturer has to do. There's another difference you see. Yeah. So what we expect here is See you on the discussion forums. Post some questions. Or send them to me if you're shy. I'm just going to do this outside because there's another class coming. So if you'd like to pack up your goods outside, then I'll see you out there.
Okay.
So we do need to vacate the room because there's another class coming.